Hello, everyone, again. Let's keep talking about the book regarding elementary physics, the brilliant book regarding elementary physics from Halliday and Resnick, the 10th edition. We're going to talk about chapter 23, Gauss's Law, problems 54, 55. 54 and 55 is what we're going to do. For problem number 54, I talk about a figure that you may or may not have access to. You may have, you may get access to the book in one form or another. If you do, there's some worthwhile problems, and that's a person's choice how they're going to approach something like that. But let me at least write some stuff here that can certainly help us out, you guys. For problems 54 and 55, let's start with 54. And 54 is saying there's a figure, and it shows in cross-section two solid spheres with uniformly distributed charge throughout their volumes. Each has radius capital R. Point capital P lies on a line connecting the centers of the spheres at radial distance capital R over 2 from the center of sphere 1. If the total electric field at point P is 0, what is the ratio Q2 over Q1 of the total charges? So they're basically telling you the total electric field, at point P. Point P is capital R divided by 2 distance away from the center of this sphere. This is sphere 1, and this is sphere 2. The charge that is totally present on sphere 1 is Q1. The charge that is present on sphere Q2 is Q2. They want us, the goal is find that ratio. If the electric field at point P, at this point right here, which is R, capital R over 2, distance away from the center of sphere 1, at this point, the net electric field that is present is 0. From these two in, vector summation, the net electric field here is going to be 0. If that's the case, can you tell me something about the ratio of the charge, the total amount of charge that is present here, 1, which is Q1, compared to what's here, which is Q2, given what they have said? They're both solid spheres, and here we're just looking at them in cross-section. They're two solid spheres with uniformly distributed charge throughout their volumes. Each has radius capital R, etc., as we've talked about. Well, we know a lot. We can say, we say a bunch of things, actually. We can say that E1, the charge associated with what's happening, well, here's, what's going on here? What is the E field at that point? Well, we're going to use Gauss's law. And the way that's going to happen is you're going to say E1 is the charge density. See, we're not, there's uniformly distributed charge densities in each of those two spheres. Correct. That doesn't mean there's the same charge density that is existent in charge 1 and in charge 2. Doesn't mean that sphere 1 has the same charge density as sphere 2 has. Okay, we're going to work under the assumption that they could very much be different charge densities. Well, rho 1, charge per unit volume, times the volume of a sphere, a Gaussian sphere, that is capital R over 2, which encompasses this guy, like that, cubed, volume times charge density, volume times charge density is charge, divided by epsilon naught. There's a lot going on here, guys. Let me kind of say a few things. Forgive the slight delay here with the setup, but let's do a little setup here on this. At least for the erasers, guys. And it's a little different than what I got in the notes, what I'm about to show. It's going to be a little more in depth regarding the whole matter, I guess you could say. This is, say, well, that's 2, that's 1. Let's give ourselves a little more room down here. When we do this, this is 4 pi r over 2 squared. Guys, we know this from Gauss's law. We know that since we know this, let's exploit the fact that we know this. This E vector dot dA vector, the integral over the surface, is E1. Because of the symmetry, it's going to be the same E field along the spherical surface of radius r over 2, of radius capital R over 2. Over that spherical surface, you're going to have the same E field, E1. So basically, you're looking at something like this, you guys, and try to give myself just a little more room. I mean, it's fine as is, but just in case. Just to kind of be for completeness here. We got E1 4 pi capital R over 2 squared yeah, that's true. The entire integral over the surface, E vector dot dA vector, well, the E vector is going to be constant magnitude due to the symmetry of the sphere over the surface of the sphere of radius capital R over 2, 4 pi radius squared, the radius happens to be capital R over 2, 4 pi times the quantity R over 2 squared times E1, that's the integral E vector dot dA vector, equals Q over epsilon naught. And that's really the logic that's taking place in something like this. Let's take a look at it. Let's kind of look at some conclusions that can be drawn when we say stuff like this. Well, do the division and see what the heck happens there, guys. Row 1, 4/3 over 4 pi epsilon naught. Okay, that's just the algebra. You're solving for E1 from right here. From what you have right here, you're solving for E1. And there's a whole bunch of ways to write it. As long as we know what we're talking about, we're okay. The 4 goes into the 4, the pi goes into the pi. The quantity R over 2 squared goes into the quantity R over 2 cubed. So what we end up getting here, guys, is row 1, R, there's a 2 down here, and there's a 3 down here. 2 times 3 is 6. Let's have a look at it, coming right there. So you grind that out, guys, you should be getting this. We grind this out, we should get to here, and that's row 1. Okay. The same exact argument is going to take place. The E field at that particular point, what's going on here? Well, it's a little different dynamic, you guys. This is a distance, capital R, and this to here is a distance 1/2 R. This is 1/2 capital R, and this whole thing is R. This is R, which is 1 R, and this right here is a 1/2 capital R. So 1 times capital R is this, and a 1/2 times capital R is this. Well, a 1/2 capital R plus 1 times capital R, a 1/2 times capital R plus 1 times capital R is 1.5 capital R, or 3/2 capital R. That's the distance here, but the E field associated, we got the E field associated with what's happening here, and it was right here. And it was right here. Here, I'm only talking about the E field associated with this. This doesn't come into play. This doesn't come into play. Because of what happens over here, we've already accounted for what can happen here. So all this right here, that shell is not going to come into play. Only this. Well, wait a minute. Then this much is outside of it. Capital R is within everything we want, and this thing is occurring at 1.5 capital R, or 3/2 capital R. And that's really the logic to the whole thing, you guys. And you can do the same exact kind of argument, guys. It's going to be E sub 2 times, and like I said, what's the Gaussian surface under consideration when you actually do it? Okay, so you got E sub 2 times 4 pi, the radius under consideration of the Gaussian sphere, we said it's 0.5 capital R plus 1 capital R, which is 1.5 capital R. All that equals rho 2. I'm thinking it's a different charge density here, guys. I'm going to work under that assumption. It may not be, but we label it something differently, and let's see what conclusions can be drawn. Here it's the entire sphere. The entire sphere 2, which is 4/3 pi r cubed to actually get that. And that's the whole dynamic there. Well, what's going on here, guys? Well, when we look at this, we got E sub 2 is, here we go. I mean, you got rho 2, 4/3 pi big R cubed over all this, which is, because if you just solve it, you're solving for E2. Divide by the Gaussian surface, the area of the Gaussian surface under consideration, divide that on each side here, and you're going to get this. And that becomes 4 pi, 9 over 4, 3 over 2 squared is 9/4. True. And again, just at this point, we do the algebra. 9 over 4 times 4 is just 9. So it's going to be 9 pi r squared. I mean, there's a lot that can happen here, guys. At the end of the day here, when we do the algebra, what's going to happen is the pi's are going to cancel. If you want, let's go over here then. Let's take the 4 and the 4 and cancel it. That's a 1 right there then. You got 1/3 right there. It's looking pretty good to me so far. You know, you got the row 2, you got the whole thing here. So you got E2 is row 2, and here we go. This is a third, this is r cubed, this is r squared. R cubed divided by r squared is r. Capital R cubed divided by capital R squared is capital R. The 3 is on the bottom. Yeah, it is. It's on the bottom. This right here flips and it's 4/9. 4/9, and the 3 is on the bottom. The 4 comes on top, the 9 stays on the bottom, and the 3 goes on the bottom. 3 times 9 is 27. And there's a lot of ways it can be written, guys. My notes, I wrote it slightly differently, but that's not a big deal. Here it is, the bottom line on this whole process. This is E2. This is E1. And given the symmetry of the entire situation, because of the symmetry here, you know, there's going to be, you know, we're pretty confident the way things are fired. Well, I mean, not just the symmetry of it, just that it's a straight out E field going this way. The only contact they're having is getting hit straight on this way, getting hit straight on that way. And if the net E field is 0, that means the E1 and the E2 are equal in magnitude but opposite in direction. Regarding magnitude, they're equal in magnitude. We just said that. If that's the case, take a look at what I have here. E1, E2, let's set them equal to each other, and I think we're in business. So, see how we can say this. All right. I mean, we've said it. I mean, we've already kind of said it. Let's be a little more explicit about it, I guess you could say. E1 equals E2. Great. Rho 1 over R. 6 epsilon naught. Rho 2 over R. I mean, rho 2 times R, rather. So rho 1R over 6 epsilon naught. Rho 2R times 4 over 27 epsilon naught. Well, there's a lot staring right at us, guys. If you divide, if this is an equation, because of this equation, we have that equation. If two things are equal, you can cancel whatever is possible to cancel. What do you say you divide by capital R on each side? And what do you say you multiply by epsilon naught on each side? Then it ends up becoming this. A lot of ways you can write it, but it's true. Okay. What does that mean? Well, it means this. Divide by rho 1 on each side, and divide by 4 over 27 on each side. Divide by rho 1 on each side. Divide by rho 1 on each side, and then divide by 4 over 27 on each side. That's just the simple algebra of the whole situation. The way this will play out, I mean, you already know where this is about to go, guys. You got 27 goes up times 6 over 4. What do you say you factor a 2 out of this one, get a 3. Factor a 2 out of this one, get a 2. The 6 over 4 reduces to 3 halves. For some reason, that doesn't look... I want to at least make sure we got that right, and we do we? Row 1, row 2. Let me back up. Let me back up 1 second, guys. I'm going to look at my, without even looking at my notes, I just don't like what I wrote. The essential argument I'm trying to make should be clear. The argument is correct. I don't like what I wrote, though. Let me just, with my luck, watch it be right, but let's just try it again here. Let's just do this again. Let's divide by row 1 on each side. If you divide by row 1 on each side, and then divide by 4 over 27 on each side, well, if you divide by row 1 on each side, you've got this left over. Then you divide by 4 over 27. That's it. Yeah, forgive my earlier foolish move regarding these things, guys. Reduce that fraction. 4 over 27 on the bottom flips upside down pretty much. You flip this upside down and put it up top. It's 27 over 4 times 1/6. True. That's 27 over 24. 3 times 9, 3 times 8. Row 2 over row 1 is 9/8. That's the ratio of the two densities. 9/8 times more dense in terms of charge is sphere 2 compared to sphere 1. 9/8 times more charge is what sphere 2 has compared to sphere 1. True. Yeah, but they didn't add, somebody could say now, okay, well, we're not done, but we're getting really close to it. Let's put it that way. Is row 2, ladies and gentlemen, Q2 over 4/3 pi r cubed. That's row 2. Is row 1 Q1 over 4/3 pi r cubed. That is what rho 2 over rho 1 is. Yes, indeed. Certainly true. Wait a minute. This divided by that is Q2 over 4/3 pi r cubed, divided by this. This divided by that is, so this divided by that is, just leave this alone, flip this. Wait a minute, they're equal size spheres in terms of volume, correct? All of this and all of this cancel, and you got Q2 over Q1. Well, wait a minute. This thing, right when you do this, it's the same. Well, it's a little easier than what, maybe I'm making it right. Basically, rho 2 over rho 1 is Q2 divided by volume, divided by the whole thing, divided by Q1 divided by volume. The volume is the same, though. That flips, the volumes essentially cancel, and you got Q2 over Q1. This thing right, this rho 2 over rho 1 is indeed the same as Q2 over Q1. It absolutely is. Why would that be? Because if you took rho 2 over rho 1, you got charge divided by volume, charge sub 2 divided by volume, divided by the entire charge sub 2 divided by volume, that entire entity divided by charge sub 1 divided by volume. The volumes are the same. Rho 2 divided by rho 1 is the same as Q2 divided by Q1. Rho 2 divided by rho 1 is the same as Q2 divided by Q1. Well, rho 2 divided by rho 1 was 9/8. And I showed it essentially, it's a number of ways you could have played the game. You also could have done this. You could have said, look, you said that rho 2 divided by rho 1 was the 9/8 we talked about. True. It remains the 9/8 if you take rho 2 and multiply by volume and take rho 1 and multiply by the same volume. Well, V and V cancel. V and V cancel, and you got rho 2 over rho 1, which is 9/8. But wait a minute. Rho times V, rho times volume, is Q. Rho times volume is Q. Put the appropriate Q there. Q sub 2, Q sub 1. Q sub 2 over Q sub 1 is rho 2 times volume divided by rho 1 times volume. Yeah, on the end of the day, that was what we already had, rho 2 divided by rho 1. Okay. A lot of ways to go around in circles here, guys. The good thing about it at the very end of the story is indeed we got Q2 Q2 divided by Q1 equals 9/8. Nine looks a little, hopefully looks like a 9, more than a Q. It's not really a big deal. Forgive me, guys, it's pretty obvious, but just in case. 9 over 8 is Q2 over Q1. And that's basically where they've gone with that. take a look at 55. We just have to be cognizant of what equals what. What is the definition of charge density? What's the definition of linear charge density? What's the definition of surface charge density? What's the definition of what's the definition of volume charge density? You know, the density per unit volume, the density per unit area, the density per unit length. We were dealing with the rhos, which is the density per unit volume. And we played the game, we got the answer. Okay, let's go to 55. Okay, guys, let's keep going. Let's go to problem number 55. For problem number 55, a charge distribution that is spherically symmetric but not uniform radially produces an electric field of magnitude E equals capital K r to the fourth directed radially outward from the center of the sphere. Here, r, meaning small r, is the radial distance from that center, and capital K is a constant. What is the volume density, rho, of the charge distribution? Okay, let's say it again, guys. A charge distribution that is spherically symmetric, in other words, at a particular layer of the sphere, we're assuming this is a solid sphere, a charge distribution that is spherically symmetric but not uniform radially. In other words, in a particular spherical shell, all the charge is uniformly distributed, and there's symmetry there. But as you move in the radial direction, either toward the center or away from the center, the charge density, the surface charge density for a particular shell is somewhat different. Conceivably somewhat different. So it's uniform. So radially it changes. Your location along a particular radius determines what kind of charge density you're talking about for a spherical shell of that solid spherical volume. That solid spherical volume, the shells, each shell has a great symmetry and uniform distribution of charge associated with it, but those densities tend to vary depending which shell you're in, what radius you're talking about. And that's what they're saying here. A charge distribution that is spherically symmetric. A charge distribution that is spherically symmetric but not uniform radially produces an electric field of magnitude E equals capital K small r to the fourth directed radially outward from the center of the sphere. Here small r is the radial distance from that center, capital K is a constant. What is the volume density, rho, of the charge distribution? So, we're going to say rho's kind of there's a little bit of a shell. I'm kind of saying surface, I'm kind of throwing it by you. It's not necessarily surface. If it's a real thin shell, it's still a volume. And let's go with that rather than surface. And you could say it's almost constant. If it's a real thin shell, it's almost constant. But it does vary. It does indeed vary, but we could say it's almost constant if the shell is very thin. And it's different all the way around. This might be easier done than said, you guys. So let's take a look. I'm going to say rho is a function of r. There's a different density. It's symmetric for any shell you want to pick. There's a symmetry. Yeah, but it's a different density for different shells, depending where you are on the radius, is what we're trying to say here. That's why I'm saying the radius is going to vary. Well, they're making this claim, and we know, again, we know a lot. I mean, we know that if you're going to go E vector dot the A vector, and you're going to get Q over epsilon naught, and there's at least some kind of symmetry here, let's say, we can say that the E field for a particular radius, this is for, I guess, guys, maybe the best way to put it is, for a particular shell, what's going on here? What's going on for a shell? What's going on for a shell? That's an interesting question in its own right. This is the E field basically at a distance r away from the center. Notice the bigger the r gets, the bigger the answer for the E field. The E field gets bigger the further away you move, according to what they're given to us here. I'll tell you what I'm going to do. We know a bunch of things here, guys, so I'm going to try to say a bunch of things here. They're saying that E is this, so because of the symmetry, we can get away with not doing an integral here. K, that's capital K r to the fourth, that's E. The area is 4 pi r squared. If you are r away, 4 pi r squared is the area. Then you got Q over epsilon naught. Well, how much Q do you have? That's a rough one. That's a rough one. How much Q do you have enclosed in that radius of small r? This is 4 pi r squared, the area around which the E field is penetrating this area. E field penetrates area, we do this, we do the integral, the whole thing. Well, it's made easy right here because of the symmetry. How much Q is there? The amount of Q is the amount of Q that's entirely present. Isn't the amount of Q that's present equal to the integral from 0 to r of the rho function? There's some kind of rho function here that we'd like to find out. True. Well, do you understand there's a rho at a distance r? The rho function is the radius at the rho at r. Yeah. A shell is 4 pi r squared area. Area times dr will give you a differential volume. Area times a differential length perpendicular to the area. This is the area, and then you're going to shoot outward perpendicular to the surface area, 4 pi r squared. You're going to shoot out a perpendicular distance, dr. dr times 4 pi r squared is the differential volume. Differential volume times rho is the amount of Q. Yeah, but that changes. First of all, the volume changes. The area changes, so you're dealing with smaller volumes. In addition to that, rho is a function of r. We don't know exactly what function of r it is just yet, but we do know this. Well, if that's true, you guys, yeah, divide by 4 pi r squared on each side. Let's see what happens here. We got kr to the fourth, they told us is the E field. They told us kr to the fourth is the E field. Absolutely. Right here. Divide by 4 pi r squared on each side. I mean, what order you write these is kind of a horse apiece, guys. Do the integral here. Well, you know, that's quite the story in its own right, isn't it? Let's see what we can do to get out of the woods, I guess you could say. There's a lot that can happen here. You're going to pull a 4 pi. You're going to pull a 4 pi out of this integral. You cannot, that's a 0, that's an r. You could pull a 4 pi out of here, but you can't pull the rho or the r squared out of there. Why? Because rho is a function of r. You can't just r, that's not a constant. The density, the charge density, changes based on location. They told us that in the problem. Not quite with those exact same words, but they told us that. Nonetheless, they told us that. Okay, that makes things a little more challenging. 4 pi and 4 pi cancel out. Yeah, true. We multiply on each side by epsilon naught r squared. R squared times r to the 4th is r to the 6th. Well, I'm not saying it's necessarily easier to visualize right now, because it's pretty intimidating stuff if you really want to think about it. As long as you believe this is true, even though we really can't solve it, or can we? I mean, at first glance, if we didn't know what was going on over here, that's it. It's not going to work. But this is mathematically true, what we've said here. To get to here, we're good. Okay, I guess, at the end of the day, guys, they were asking you for what is rho? At the end of the day, they're asking, please solve this. Okay, then maybe I do have a way out. Maybe I do have a way out for this thing to work out. For this right here, I know that at zero, at a radius r equals 0, put a 0 right here, it's 0. And then anything else is going to go more than that. So there's a real symmetry here. I'll tell you what I'm going to do. How would you do this? Basically, guys, I mean, there's a lot more to this than what I'm about to say, but let me just say it. Here's the integral of a function. The integral of a function differentiated gets you back to the function, and that's what's going to get us out of this. We're going to take the derivative with respect to r on each side. We're going to take the derivative with respect to r on each side. Here it goes. If two things are equal, they remain equal if you take their derivative. Capital K and epsilon naught are constants. The derivative with respect to r is just you're getting this derivative and keeping the constants involved. Derivative of r to the sixth with respect to r is 6r to the fifth. We have 6r to the fifth times kappa epsilon naught. So it's your choice how you want to write this actually. 6k epsilon naught r to the fifth. The derivative of this guy, the derivative of an integral is just the item that was being integrated written down. True. Rho r squared. Believe it or not, guys, we're really close to it now. If you want to find rho, what do you say you divide by r squared on each side? Rho of r is going to be rho of r is going to be all this divided by r squared. Divide by r squared on each side. 6 kappa epsilon naught r to the third. That is it. Six K, shouldn't call it kappa, it was not really kappa. But you understand, I mean, this is it. Should not have been right. Right, okay, sure, absolutely. That's it. Yeah, it really is true. It really is true, guys. I mean, there's your answer. There's your answer. You had to go about it in a very, I think we had to do it in what I think and the way that the instructor's solutions manual is proposing for us to look at it. They went about it in a very nifty manner. And they're right. This is right. This will work. This will work. How do I know it'll work? I mean, that's a good question. How do you know it's going to work? I'll tell you why I know it's going to work. The E field at any distance r, is this. You could say, so what? Yeah, you're not telling me much on that. All right, I'll tell you more. You saw this. E field, because of the symmetry, E field times area equals charge over epsilon naught. Here's the charge. Each volume of a shell times the rho for that particular shell. And the rho is different for every single, according to what's going on here, according to what we found. In this case, we know that the charge density varies. It is symmetric about any particular shell, but when you go, for any shell, no matter what shell, there's symmetry there. Great. There's uniformity there. Symmetry, uniformity, it becomes a linguistic argument at some point, guys, but yes, whatever, but when you change shells, the charge density changes. Didn't we say when we did this whole thing, didn't we say that the integral from 0 to r, that was a rho. I'm claiming the rho, ladies and gentlemen, is 6k epsilon naught r cubed. 6k epsilon naught r cubed. Okay, that's a claim being made. It's a claim being made. Now, guys, I don't know how, again, I don't know how good the video is on that, but here's the rho. Rho is 6k epsilon naught r cubed. This is r cubed right here. R cubed. It's going to go through there. Okay? Okay, so what? Well, why don't you do the math? Let's just see what happens. Let's just see what we can say. We've got kr to the fourth. Well, no, I'm not. You know what? I tell you what I'm going to do. Please let me get away from that. I don't. I know it's going to be kr to the fourth, but I tell you what, guys, I'm going to pretend I don't know. We know that E equals capital K r to the fourth. E equals capital K r to the fourth. We know that. They told us that. Yeah, okay, whatever. Let's pretend we don't know it. Let's pretend they gave us this. Let's pretend they gave us this first, and instead of asking us, they initially gave us what E was. They told us that E was this, capital K r to the fourth. They gave us that, and they said, okay, I gave you that, solve for a rho. Solve for rho, and we did. What if they gave us rho first, and they said, solve for E? And you don't know that E's equal to this. You got to prove it. Well, I'm going to say integral over a closed path, E vector dot dA vector, equals Q over epsilon naught. Because of the symmetry, the integral E vector dot dA vector is E, the E field, as a function of r it's going to be, times, at a particular place, with Gaussian surface, 4 pi r squared. 4 pi r squared, what's the E when you got 4 pi r squared as a Gaussian surface? Well, E times 4 pi r squared as the Gaussian surface equals charge over epsilon naught. The charge, the total charge, enclosed within this Gaussian surface of 4 pi r squared, so E times the area of the Gaussian surface enclosing the charge, this is the area of the Gaussian surface enclosing the charge, times E for the E passing through, right as it passes through the Gaussian surface of area 4 pi r squared, enclosed in the 4 pi r squared is charge divided by epsilon naught. This is the density function. Rho is 6 capital K epsilon naught, those are all constants multiplied together, times r to the third. 4 pi r squared times dr is the differential volume. This is dV, differential volume. 4 pi r squared dr is differential volume. Differential volume times the charge, the volume charge density. The volume charge density at a particular radius times the differential volume at that radius gives you the amount of charge that is present in that shell, in that differential volume located a distance r away from the center. That tells you how much charge is present in that differential volume, in that small, very thin shell that has a radius of r. So 4 pi r squared times dr is differential volume times the radius, volume times charge density per volume. Volume times volume charge density. Volume times volume charge density is going to be the charge. Do the integral, you get the total charge. Well, I don't know, man. That's a whole speech I just delivered. Guys, remember, we are going to get that for an answer. Just leave that alone. Pretend we don't even know what that is. What do we got? We got 4. We got E 4 pi r squared. Okay, we did all that business. Integrate this thing. It's a lot of stuff to integrate here, guys. I mean, there's 6k epsilon naught times 4 pi. Right? Yeah, absolutely. I mean, 6k epsilon naught times 4 pi, r cubed times r squared is r to the 5th. The integral from 0 to r and that's that. Okay, sure. Well, let's do it. Do this integral, you're going to get 1/6 r to the 6th. You're going to get 4 pi, you're going to get 4 pi r squared times e. You got 6k epsilon naught 4 pi. All multiplication going on here. You got 1/6 r to the 6th evaluated between 0 and r. Well, you put a 0 in here, it's 0. You put an r in here, you get the same thing you got right there. So that looks pretty good. Here's kind of the fascinating thing about the whole thing. 6k epsilon naught 4 pi 1/6 r to the 6th divided by 4 pi r squared. Well, 1/6 and 6 cancel. 4 pi and pi cancel. Right. For some reason, guys, I'm just trying to think what is going on here. 6 r squared r to the 4th. Right. For particular, there's got to be something else here, guys. There's 6k epsilon naught. The 4's cancel, r to the 4th. Because of the symmetry, tell you the total charge enclosed. For some reason, guys, I'm getting close to the answer, but not the answer I'm supposed to get here, and I'm trying to think what could be doing that. the Gaussian surface. And for some reason, why is that not coming out, guys? Forgive me here. Right. You know, I'm actually looking at this and it's coming out. Yeah, it's all this divided by epsilon naught, forgive me. There's an epsilon naught right here. There was an epsilon naught right here, guys. Sorry about that. Epsilon naught right here. There's something else actually there that was kind of where I was kind of losing it here. But okay, let's just cut to the chase here. E is, you know, this guy can't, you know, the 6 and the 6 cancel. 1/6 and 6/1 cancel. The epsilon naught cancel. The 4 pi and the 4 pi cancel. R to the 6th divided by R to the 2nd is R to the 4th. We've got, yeah, it was so obvious it was staring at me, guys. Sorry I faltered on that. I didn't want to say anything until I needed to say something. Here's what it is. That's the E field. That confirms it's true. This row of R, this row, which is a function of R, equals 6 capital K epsilon naught R to the 3rd. If that's true, you can plug it into Gauss's law for electric fields and do the right evaluation, and you'll actually find at the end of all that the E that they were actually talking about, the E way over there, which is equal to capital K R to the 4th that they were talking about, that we used to find rho of R, rho which is equal to rho of R, which is equal to 6 capital K epsilon naught R to the 3rd, that got us, that we were able to find what rho is based on what they told us. Put another way, had they not told us that, but told us this, could you plug this rho right here times the differential volume element, 4 pi r squared dr, do the integral, which will give you Q. Q divided by epsilon naught is the E field times the area that encloses the charge. The E field times the area that encloses the charge equals the total charge. The E field times the area that encloses the total charge under consideration is equal to the total charge divided by epsilon naught. Well, because of the symmetry of the situation, we did not have to use calculus here. We did not have to use calculus here to evaluate this. We just said E times 4 pi r squared equals the integral from 0 to r of the rho function, pretending they gave us the rho function first and not giving us this first. We have to prove this. We already went the other way. We proved what rho was when they gave us this. And I said, okay, look at what we just proved. Pretend that is what they gave us first. Can we prove that this is true? Now pretend we don't know that. Integral from 0 to r of rho times the differential volume element, 4 pi r squared dr over epsilon naught. Do all the mathematics here, and indeed, you get E equals kr to the 4th. So a little extra regarding that particular problem. All right, guys, thank you very much for your time.